So let's consider the same function as before, f of x equals x squared, over the same interval, 0 to 2. But instead of taking a right Riemann sum with exactly 10 rectangles, let's take a right Riemann sum with an arbitrary, unknown number of rectangles. Let's just call it capital N. Let's find a formula for the estimate given for us for the area by this Riemann sum. Now the process starts the same as it does before. Try and identify the values of A and B that we're dealing with. And then use that to identify the width of each of our rectangles. Delta x is equal to 2 minus 0 over the number of rectangles that we have. Now, unfortunately, for us, the number of rectangles is a variable. So we'll have to leave delta x in the form 2 divided by capital N. Likewise, for the height of rectangle K in this sum, we can get this by plugging in the right endpoint of rectangle K, the right half. 0 plus delta x times K, but unfortunately, now delta x is 2 over n instead of something as nice as 1/5. So when we go ahead and work on simplifying this, we're still going to have an expression that contains the letter n in it, 4 over n squared, k squared. And when we do our summation, summing from k goes from 1 to now not 10, but however many rectangles we have, of width 2 over n times 4 over n cubed, k squared. In this case, we're still going to have to deal with this capital N. But what saves us is that n, even though we don't know what number it is, n does not depend on the value of k. So just as we did with 1 over 125 in the previous example, this constant can be pulled to the outside, and we can leave 8 over n cubed on the outside and deal just with this formula in the back, sum as k goes from 1 to capital N of k squared, which, as we have seen, simplifies to n plus 1, 2n plus 1 over 6. So this right here is a formula that we could use to find the value of the right Riemann sum using any number of rectangles somebody wanted to use. If someone wanted to use a tiling with 100 rectangles, then we could plug n equals 100 into this formula. If someone wanted to use 1,000, 1,000,000, 1,000,000,000 rectangles to tile that region, then we could figure out what the result would be by plugging in that value of n into this formula. And better yet, we can actually calculate the limit of this formula as n goes all the way to positive infinity, in a sense using infinitely many rectangles to tile the region. Now, this is the moment where we have to go back in time to either pre-calculus or calculus, when you studied how to take limits of rational functions for the first time. The key is to look at the leading terms of the numerator and denominator. In the numerator, our leading term would consist of an 8, an n, and a 2n. In other words, 16n cubed. In the denominator, our leading term would consist of an n cubed and a 6, so 6n cubed. And so, the beauty of this is that those n cubes cancel, and we're left with the number 8 over 3, 8 thirds. And as it turns out, that by letting the number of tiling rectangles grow infinitely large, we actually get an exact value, the exact value of the area under f of x equals x squared. No longer an estimate. When we take the limit and use infinitely many tiling rectangles, that estimate becomes perfect, and we have exactly calculated the area of that region.